Okay, hello everyone. Thank you for coming to this webinar. We'll wait an extra minute just to make sure everybody that wants to attend is here. We're happy to be joined by Antonio Pellegrino, a professor lecturer at the University of Bath. I had the pleasure to visit their lab not too long ago.
Thank you, Antoine.
I'm going to ask you, Antonio, do you have your webcam on? Or am I just
Now it should turn on. Yes.
There we go. Okay, great. Hello.
Hello.
Great. So I see quite a few more people came in. So that's great. Let's get started. Before we, I'll introduce myself. I'm Antoine Dumont, one of the field application engineers, scientists at Telops. I've been with Telops for 2 years now, working on plenty of different, very fascinating applications. Among others being experimental mechanics, which is the topic of today's webinar. And I'll be joined by Antonio here, lecturer, like I said, at the University of Bath. I'll let you introduce yourself briefly here.
Hello, everyone. My name is Antonio Pellegrino. I'm a lecturer in mechanical engineering at the University of Bath with a research interest in particular on dynamic behavior of materials. So on the behavior of material when deforms very quickly, very fast. And well, today the topic of today is assessing how the speed of deformation and the history of the deformation affects stress distribution within samples in dynamic tensile high rate testing.
Great. Well, thank you very much. So I'll get started very soon. We always like to start our webinars with a little poll. So something will appear on your screen, and feel free to just click on the answer that describes yourself as best as possible. So here we are. Just to have an idea of what kind of audience we're dealing with here. If you have no direct experience with the technology, no direct experience, but you've considered infrared technology before, some experience collecting or processing some data, or you even consider yourself a thermal imaging expert.
Well, it would be C, yes.
Oh, sorry, I'm talking to the rest of the audience, but
okay.
Yeah, I believe you're somewhat of an expert in this case, Antonio. Yes.
Okay.
So we'll give another maybe 10-15 seconds. Great. Okay, so I'll close the poll and share with everyone. We can see that it's a pretty diverse crowd that we have here. Quite a few people that don't have direct experience, probably people from the field of experimental mechanics interested in the topic of today's webinar. That's great. And other people that do have considered it, and some that do have some experience collecting data. So that's great. Look forward to some questions from everyone. So there's no dumb questions. We're always welcome any kind of question that you might have. Okay, so let's get started. I'll start by simply, I just want to make sure you do see the presentation. Yes, here we go. So today I'll give a quick introduction to Telops. Those of you that are not familiar with our company, I'll give a quick application overview and some interesting case studies that I worked on in the experimental mechanics field. And then I'll let Antonio talk about today's very specific topic on the strain history during the impact of strain history during high rate loading. So a quick overview for Telops. We started in 2000 in Quebec City. We're still in Quebec City nowadays, and we do employ over 100 employees, most of them in Quebec City, but people do work in the United States and in Europe as well. So we just celebrated our 25th anniversary. That was a great event. We're very proud to have been working in that field and having established ourselves as world leaders for thermal infrared imaging solutions. We do offer even aerial methane service. So it's a leak detection service that works really, really well. It's been expanding quite a lot in the last few years. So if that's something that's interesting to you, but obviously not in the experimental mechanics field. We recently acquired LRTech as well, so an interesting line of hyperspectral products. So a quick overview of our product line. I won't spend too much time on this. The topic of today is really focusing on the high performance fast cameras that we have here. But we do have hyperspectral cameras, so a nice spatial resolution with a spectral resolution that we have for every pixel. So every pixel that you have in your image does contain a three-dimensional information with spectral data for each of them. Multispectral cameras, sort of an in-between hyperspectral and broadband cameras, where we have the core being a broadband infrared detector, where we have a filter wheel with 8 filters that rotate, so we can acquire simultaneously 8 different windows at different spectral bands. We have high dynamic range cameras. The new one, the M700, is particularly interesting, a whole new category, really a revolution in the technology for this kind of camera. So I invite you to look at our notes or webinars on the topic. Then we have our fast cameras, which we'll talk about more today, and our entry-level radio cameras. So our interesting new cameras, so of course, cheaper than the other products, but that have the same high accuracy calibration that Telops is happy to offer for every camera. So this one, the V60, is the microbolometer, and we have an M100, which is also cool, but in a different way than the high performance cameras. So we do cover plenty of applications with Telops cameras. So infrared can be used for measurements in all of these fields and more. So ballistic, combustion, of course. Today's topic on experimental mechanics. When we talk gas detection or mineral identification, that's more in the realm of hyperspectral imaging. IR signature is a sort of broad category that applies for anything that has a thermal or spectral signature. Additive manufacturing is the one maybe closer to experimental mechanics. That's when we try to understand the properties of materials that we use for additive manufacturing. Cold spray is part of that family as well, if you're familiar with this. And non-destructive testing is an interesting one where you can try to detect defects, different parts that have different emissivities on surfaces and inside those materials, if you can have a proper system for non-destructive testing. But of course, today we'll go over experimental mechanics, maybe a bit more in detail. So I have a few examples here of some measurements that we acquired with our fast cameras. A classic example being the split Hopkinson bar. So Antonio is very familiar with this, of course. But with our cameras, in experimental mechanics, typically you want to go as fast as possible to understand the process in that high rate loading or tension system. So this is an example with the M3K, the fastest infrared camera that we have, also the fastest camera really on the market. So that was done at 43,000 hertz. So the playback that we see here is at 0.0004 times the real speed. So a nice information on the thermal, so the heat release of that process, the dislocations creating that temperature increase. So we have, of course, a lower resolution at that speed. You can also use higher spatial resolution cameras. So this one's a 200 HD to have a bit more spatial information on those systems. Of course, you won't be able to go as fast with those cameras. And that's an example of a new method in our software that adds a contrast enhancement. So it can really see the particular contrast that is happening in the system. And when you zoom in, you can see every pixel, you can see that contrast very, very well with that mode. Another kind of process that we can observe with infrared imaging are all those peculiar phenomena that does happen in experimental mechanics. One of them being the thermoelastic cooling effect that was proposed by Lord Kelvin a long time ago, but that was just observed experimentally for the first time just a couple of years ago with my colleague Joseph Carrick in the United States. So that's a really interesting process and phenomenon that they do describe more in detail in the webinar on the topic. Going back to a split Hopkinson bar, I did some tests in Germany as well last year on an aluminum magnesium alloy. If you're familiar with that field and those types of materials, you might click that the PLC effect is likely to occur here. So the Portevin-Le effect, named after two French researchers, I believe. So that's where we see those bands of dislocation moving up and down your sample. And with an infrared camera, you can actually see those bands moving really, really well. And you can see that heat, the energy release from those dislocations happening in that material. So it's a beautiful phenomenon that you can observe perfectly well with those types of cameras. Typically, people will use digital image correlation, where you can see here, seeing the strain history of those materials, not strain history, but the strain being increased with those bands on the material surface. We can actually correlate digital image correlation and thermal imaging as well for those kinds of measurement to get really a full picture of the process. So we're able to do a little bit more analysis, seeing really that temperature displacement in the samples. That's the kind of setup we had, flipping the camera on its side to have the longest measurement range. And also they were particularly interested in the fracture point, where we had that double fracture, so double heated point at the fracture. And you can see there's a difference in temperature depending on how the sample is being displaced, what more strain in a particular spot. But a lot of information being able to be collected with that kind of imaging in the experimental mechanics. There's lots to do. I wanted to mention microscopy imaging as well. Not everyone does macroscopic kind of samples and imaging in the field. Some people do experimental mechanics on a microscopic level, and it's possible to do infrared imaging in that range just as well. With those microscope lenses, we have a G1X and 4X, and we can see some very nice grain structures on a surface here, so 2 microns on average for those grain size. And the inside of optic fiber here very well, not particularly experimental mechanics related, but we can see very, very well the core of that optic fiber that's only a millimeter wide. And here is just a prettier example of a housefly discal cell, so just the tip of a wing of a housefly, seeing every cell that's on the image here. That was done in infrared just as well. And finally, I'll let Antonio speak very soon, I promise, but I just wanted to mention the new radio cameras. So we have the V60 and the M100. They're also just as interesting for experimental mechanics when you're not dealing with high-speed phenomena. So you'll be able to get that really, really precise temperature measurement with these, not at particularly high speed, so between 60 and 100 hertz, but you'll be able to detect very, very precisely those thermal heating phenomenon just as well. The V60 being in the long wave part of the spectrum, and in the M100 is in the mid wave part of the spectrum. So particularly interesting for high temperature phenomenon and experimental mechanics, high speed measurements, semi-high speed measurements, I should say, for the M100. So they're very, very small compared to our standard fast cameras. They really fit in the palm of my hand, these two cameras. So perfectly well suited to be incorporated in setups that are a bit difficult to combine with those bigger cameras. So that's it for me. I really appreciate Antonio being here today with us. So I'll just give a quick bio for Anthony before I give him the reins of the presentation. So Antonio, like I said, is a lecturer at the University of Bath in the Mechanical Engineering Department. He really specializes in the development of novel experimental apparatus for measuring the mechanical response of engineering materials at high strain rates. So recently, he led a project focusing on the development of a combined tension torsion Hopkinson bar capable of controlling the timing and amplitude of direct and shear stress pulses. So his research also is interested in AI, so artificial intelligence in materials modeling. That's also a very booming field in many fields, I should say. So he's part of that team at Bath for academics developing impact engineering facilities to study the dynamic response of materials under extreme temperature conditions with a particular emphasis on the cryogenic regime. He's currently a member of the governing board of DIMAT, the leading European research association in the field of dynamic behavior of materials and its application. So thank you very much again, Antonio.
Thank you for the kind introduction.
Pleasure. So I'll give you Lorraine being the presenter, so you can share your presentation now.
Can you see my slides?
Yes, perfect.
Perfect, thank you. Well, good morning, everyone, or good afternoon for those of you who are connected on the other side of the Atlantic. My name is Antonio Pellegrino. I'm a lecturer in mechanical engineering at University of Bath, and today I have the pleasure to share with you a previous research I've conducted with my former PhD student, Dr. Govin Gower, who is now a postdoctoral researcher at University of Oxford. This particular research focuses on the influence of strain history and adiabatic heating on the dynamic strain localization and stress axiality during high strain rate tensile loading on ductile titanium alloys. I will take a couple of minutes, a brief introduction about my research. My expertise revolves around the understanding and researching on the dynamic behavior of different materials. I've done quite extensive research on titanium alloys, composite and reinforced polymers. Particularly interesting for me are syntactic foams, which are polymers with dispersed microballoons with different characteristics. I've also conducted research on additive manufactured materials and structures with different industrial and academic collaborators. And as Antoine mentioned, I've also been involved in the development of advanced experimental techniques for understanding the behavior of materials under realistic loading condition under dynamic loading. I've also had some interest in the development of machine learning data-driven models. So there are models that are built based upon the experimental data directly translated into relationship between stress state, temperature, and strain rate. And I've also conducted some research in biomechanics, in particular in eye mechanics. So very quickly, oops, slideshow. For some reason, it doesn't want to. Okay. So can you see my slides?
It's not in presenter mode. You have the whole PowerPoint window, and it's quite a bit small.
Just a second. I don't know, for some reason. I'll close this one, and I'll share again. Well, I will try to go in presenter mode again. Slideshow, current slide. Okay, seems to be working again. He was quitting automatically, but okay. Hopefully little disruption, but not major one.
No worries.
So recently I've investigated the behavior of with collaborators, and I have investigated the behavior of materials under combined tension torsion loading. Here you can see some of the most representative results. This is a recent paper just published this year, where we have investigated the effect of strain rate and temperature on the failure stress locus and dynamic behavior of asymptotic foams under different combination of load, where we had compression, tension, torsion, and combination of tension torsion. So we could investigate, as you can see in this figure on the bottom left, how the strain rate is affecting the locus of stress that define the failure of the material. In blue, you can see the quasi-static behavior, and in red, the dynamic behavior. And we have done the same thing also in terms of temperature. You can see how the dynamic response is affected by temperatures. In light blue, the failure stress locus at minus 25 degrees, and then at room temperature and 75 degrees. These are polymers, so highly sensitive also to temperatures. A lot of effort has been also devoted to synchronizing and timing arbitrarily shear and longitudinal stress pulses using ultra high-speed piezo actuators. And we were able to synchronize stress pulses, but also design stress pulses, the history of stress pulses, where we have tension and torsion synchronized, or longitudinal stress preceding torsional stresses, or vice versa, and with an accuracy of tenths of microseconds, which is quite remarkable if we think about the wave speed of longitudinal and shear stress waves that is in the order of 1,000 meters per second. At the University of Bath, I'm part of a team of academics that is developing a new impact engineering facility that is will be capable to measure the dynamic behavior of materials down to 20 Kelvin. Here you can see some photos of a recent visit from Telops, where we have measured the adiabatic heating during a high rate compression experiment, and particularly in the first video on the left, under repeated stress pulses, where we had wave reflection and then reloading. So we could see the temperature jumps for each of the loading, unloading, and reloading. Now, going back to the main topic of today, and going from a very general point of view, when we have an impact problem, we cannot solve it directly by the creativity of a designer and in the real world. So as probably all of you in the audience know, we have to pass via numerical and analytical methods and find a virtual solution to the solution in the real world. However, this virtual solution cannot prescind from accurate and reliable experimental data. And typically, the most common data that we can get for a material come from tensile tests. However, when these tensile tests are conducted at high strain rate, meaning that the material will deform and fail in a time of approximately 200 microseconds typically, the mechanics and other physics, such as thermal properties, become coupled, and the analysis becomes more sophisticated, and some challenges in the analysis of the data may arise. If we go back to the basic of experimental mechanics, when we have necking, when we have non-homogeneous strain distribution, image after image, if we look at the strain distribution along the gauge length of the sample, we notice, for example, in this graph on the bottom left, that strain localize around a certain section until failure. Here in the DSE in red. And why is that important in experimental mechanics? Well, before strain localization, we can assume that what we measure experimentally as a true stress, so as a ratio between the measured force and the minimum cross-section of the sample, is coincident with the equivalent stress. So that is what we are going to input in our finite element software to simulate the behavior of structures. However, once necking occurs, we have a development of a distribution of stresses that is not only uniaxial, but we have a distribution of axial, radial, and loop stresses. Therefore, the equivalent stress strain curve is going to be different from what we can measure experimentally. It's going to be different from the curve that can be found out by using experimental diagnostics. And therefore, we need to correct for it. Now, the question that we try to, and we answer with this research is, do strain history and strain rate affect the stress state in ductile alloys during high rate loading? And to do so, we have conducted a series of experiments. First, we preconditioned the samples of titanium 64, perhaps the most common titanium alloy used in aerospace, at the 3 different levels of restraint using real-time strain control. In particular, we use the Emetron video extensometer that allowed us to control in real time strains. And then therefore, well, afterwards, we also verified the strains with other DSE methods. And we applied these 3 levels of restraint to precondition, preload, predeform the samples and assess what the effect of strain history and as a consequence of adiabatic heating is on the triaxiality of the sample. After we precondition the sample, we predeform, we conduct a series of high strain rate experiments on the split Hopkinson tensile bar. For those of you who may not be familiar with this apparatus, I will describe it quickly. In this apparatus, a projectile is pulled by a hook and a piston to impact a flange that is connected to a rod. Upon the impact of the projectile on the flange, a stress pulse is generated and propagates along the rod and the input bar until reaching the interface between the input bar and the sample. At the interface, part of the stress pulse is reflected back to the input bar and part of it is transmitted to the output bar. It can be demonstrated by a stress wave analysis that we can work out what are the velocities and the forces at the interfaces using from the stress history measured on different locations of the bars. To visualize also what happens during the deformation at very high speed in the samples, we have also used ultra high speed camera. In this case, was a specialized imaging Kirana to monitor the contraction of the neck during tensile loading at high strain rate, and the infrared high-speed Telops M3K camera in conjunction and synchronized between each other. Before we conduct the experiments, of course, we conduct a calibration with known temperatures, using calibrated thermocouples in the range of temperature we are expecting to measure with the infrared camera, so that we could calibrate the emissivity of the instrument and trust measurements we were going to conduct. At the same time, each and every experiment conducted on the material we were testing were verified for dynamic force equilibrium. With this let's say experimental check that is more important for soft material, but also important for metals when we are pushing high strain rate, we check that the deformation along the gauge length is uniform, and that therefore what we measure experimentally is actually representative of the material itself and not only of a portion of it. So we conducted a series of experiments on different samples, pristine samples, but also samples that were pre-strained at 6%, 10%, and 14% quasi-statically. And we monitored typically at a frame rate between typical 500,000 frames per second, the diameter contraction of these different samples with different preconditioning, pre-deformation. And we can see here that the diameter evolution tells us already something. We can see that diameter evolution is different, the slope is different when we test pristine samples and for increasing levels of restraint. And also, and particularly at the high levels of restraint, that there is a kind of a plateau area before the diameter contraction drops. This gives us already an indication that the strain history has an effect on the stress triaxiality, and also that this may be related to adiabatic heating. Indeed, when we take and export the data from the Telops M3K camera, we found out that when we tested pristine samples, the increase of temperature was quite substantial and higher than the increase of temperature measured when we had different levels of pre-strain. We could see, if we look only at the maximum value of the temperature increase, we can see what we were expecting beforehand, but we couldn't demonstrate experimentally before using this equipment, that the increase of temperature is inversely proportional to the level of pre-strain. And that is, as all experimentalists would expect, is because of the plastic energy that is dissipated during the deformation. As the experiments occur in a very limited time, it cannot be dissipated in the surrounding environment. When we have predeformed sample, the amount of plastic energy that has to be dissipated is smaller. The increase of temperature is also smaller. Here in this high-speed photo, you can see a parallel between what we measure with the conventional high-speed camera and with the infrared Telops M3K camera, with the increase of temperature for pristine samples in the region of 210 Celsius degrees. So we were interested about the stress reaxiality during these experiments, but this cannot be really measured experimentally. There's no way to measure experimentally the distribution of radial stresses and loop stresses in the sample. So we needed to reproduce as accurately as possible what happened in the experiments numerically. To do so, we have used LS-DYNA software, and we prescribed first boundary conditions displacement on one end of the sample that were exactly representative of what were applied in quasi-static and Einstein rate condition. So this is what you see in purple is actually the velocity, the difference of velocity between the two ends of the input and output bars. And then we use the most usual constitutive law for metal. It works for titanium 64. We use the Johnson-Cook constitutive model, where we can measure the dependency of the stress in the material from the plastic strain in the first parenthesis, from the strain rate, second parenthesis, and from the temperature in the third parenthesis. The simulations were fully coupled, and we took into account of the adiabatic heating prescribing a level of Taylor-Kinney coefficient that tells us how much of the plastic energy per unit of volume is transformed into heat. Now, how did we make sure that we could trust what happened in the simulation being representative of the experiment? We have conducted a multi-factor optimization of all the parameters in the simulation using LSOPT, and we made sure that not only the global response of the material in terms of force and displacement was matched exactly by the simulation, as you can see here in the top right diagram, but more importantly, in this particular research, that also the local behavior was matching between the numerical and experimental data. In particular, the diameter contraction was matching for each and all of the levels of pre-strain. And of course, the adiabatic heating temperatures was also matched by the sample, by the simulation. At this point, with all the diagnostics that we could possibly use, matching between numerical simulation and experimental data, we could trust that what we extract from the simulation is actually representative of what we measured experimentally. So at this point, we could focus on the stress distribution on the necking section. And extracting the stress data along the radius of the sample, considering the material isotropic in this case, we could extract the distribution of radial stresses and axial stresses for different level of pre-strain at the instant of macroscopic strain. And we could see that this distribution of stresses, for example, if you look at radial stresses, the variation is larger when we add pristine samples, and it decreases for increasing level of pre-strain. And the same thing is for axial stresses. If we increase the level of pre-strain, this distribution of stresses becomes flatter and flatter. So indeed, we have an effect of the strain history, and due to adiabatic heating, that is affecting the triaxiality. Now, as experimentalists, why do we care about that? Well, we care because the difference between what we can measure experimentally, the true stress, and the equivalent stress is inversely proportional to the level of pre-strain. So it's maximum on pristine samples, here 71 megapascal, and it decreases for higher level of pre-strain. And if we go back at what we said in the beginning, this is important because eventually, when we input the data in our finite element code, we need to provide equivalent stress strain curves. Of course, this is not a new problem. It has been investigated historically and across many years, particularly quasi-statically. The most common correction factor for triaxiality is the Brigman correction that relates true stresses to equivalent stresses as a function of the geometric properties of the necking profile. So this correction requires evaluating the radius of curvature of the necking profile and the minimum, knowing the minimum cross-section radius of the sample. It is quite simple in terms of formulation, but it requires some direct measurement of the shape of the sample. There are more complex and more recent formulations. One of them is the Gromada semi-analytical correction factor, which also relies on the knowing what is the ratio between the minimum cross-section radius of the neck and the radius of the necking profile, as together with the ratio between the original initial radius and again the minimum necking radius. Other correction factors are very popular, in particular this one, the MLR polynomial, because that doesn't require the measurement of the necking profile, the geometrical properties of the necking profile. It only relies on the difference between the equivalent plastic strain and the equivalent plastic strain at the onset of necking. Therefore, once we know for a different state of deformation this difference, we can work out what is the ratio between equivalent stress and true stress. This has been proven for various metal alloys. The question is it affected by high strain rate condition? Does it still work? And how accurate it works at high strain rate condition? And I mentioned a few slides ago that some correction rely on measuring the profile of the geometric properties of the profile of the necking section. There are also other formulas that help us to estimating the shape of the neck without relying on direct measurement. Some of them are listed here. Leroy and Fengdu provided a couple of equations that allow us to work out to estimate the shape of the neck, only knowing the level of strain on the sample. So now that we listed all these corrections, it's time to evaluate it. We evaluate on the left, you can see all the different type of correction, both relying on the direct measurement of the shape of the neck and on analytical data, with respect to the ground truth of the integrated experimental numerical data that here is in the red curve arrowed here. You can see some of the correction actually do an excellent job. In particular, the black curve here, the MLR correction, does a very good job in approximating the ratio between equivalent and true stress. But when we look at high strain rate, and here I'm looking at high strain rate experiment on pristine sample where the difference is maximum, we can see that there is a discrepancy between the different correction factors and the experimental data that again confirms that there is an effect of strain history and there is an effect of the adiabatic heating on the stress distribution. So when we look at this data, we said, okay, let's see if we can modify one of the correction factors to take into account of these factors. So we use the original MLR formulation and we pre-multiplied by a multiplication factor that takes into account of the level of pre-strain and of the thermal properties of the material, Taylor-Kinney coefficient, specific heat, and density. And we all these via two parameters A and B that are constants and need to be calibrated. We did this calibration using all levels of pre-strain. So to take into account of all the strain history, not only of the monotonic experiment on pristine samples. And we found the optimal A and B parameters that could fit and reflect what happens in the experiment. So you can see that dynamic MLR curve matches very well the experimental data. Now, this is pretty obvious at this point because, well, not that obvious, but we adjusted an available correction factor with our data, and we calibrating with all this pen, we matched it. Now the question was, does it work for other titanium alloys that have similar thermal and density properties? That would be a more valuable correction factor. So we assessed this formula with the A and B parameters we found on titanium 64 or another titanium alloy. So we tested this modified correction curve on titanium grade 9, so titanium 3 aluminum 2.5 vanadium, which is another available commercial alloy, at a wide range of strain and strain rate, and assessed what is the error between what we could measure integrating experiments and numerical data, and what is the result of the correction factor. And we found that for all this range of strain rate from 12 to 2,700 and range of strain between 0.05 to failure, these are true strain, by the way, the maximum error was 2.51%. So we felt confident that the modified MLR correction is applicable for all titanium alloys, for as long as the thermal properties and the density are similar between different alloys. Once we calibrate the constants A and B, we can apply the same correction to similar alloys. So for example, if we were to use copper alloys, once we calibrate for one A and B for one alloy, we are confident that we can use the same coefficients A and B and correct for the dynamic MLR to find an optimal correction for triaxiality. To conclude, we have conducted an investigation that indicates the influence of strain history and adiabatic heating on the stress state in the neck region. We have used a combination of experimental, analytical, and numerical methods to show the need to introduce thermal effects in stress triaxiality correction. And we verified the validity of this correction for different alloys, at least of the same nature. Now, current research next step is to applying similar methods on materials that show anisotropic necking. For example, one first material we look at was commercially pure titanium grade 2 bars that were processed such a way to show high anisotropic behavior. And this setup, this has to be done using multiple camera setup or at least a twin camera setup and a particular procedure to work out what is the assuming that the neck is elliptical, to work out what are the axes A and B of the ellipse. That is everything from my end, and I'm now available to reply any of your questions. Thank you.
Great. Thank you very much, Antonio. I'll invite everyone to ask your questions in the question tab you see towards the bottom of the menu, on the GoToWebinar menu. While I don't see any questions right now, I forgot to mention it at the beginning, but if you want to take your time to write down your questions, we'll answer them as soon as possible. In the meantime, I do have a question for you. In terms of the experimental setups, you showed those speckle patterns on the samples and the IR images at the same time underneath. Did you do the measurement on those samples with those cameras simultaneously? The IR images, were those images from the speckle samples, or were there different samples with an IR paint but with the same level of pre-strain?
No, they were captured at the same time.
At the same time, okay. So you had a fairly uniform surface. So the emissivity question, that's what I'm wondering.
Yes, so the speckle pattern was before we conducted the experiment, we made sure that it was quite uniform, so there was not a dark area or a brighter area in the sample. I have to say also, quite a bit of research was also on finding the right paint to follow the neck. So it may sound trivial, but a lot of trials were done to find a stretch paint that could follow the neck without detaching from the sample.
That's always a bit tricky. It's difficult to do proper measurement when the paint chips, and it does happen often.
We found eventually that the best performance was given by not by simply acrylic paint that was already made, but something that we needed to mix separately and find the optimal proportion to make it more stretch.
Interesting. You added a certain polymer to it?
No, not really, but it's key to find the right proportion of water and paint. Basically.
Oh, I see. Interesting. Yes. Okay, great. Thank you. I have one question here. A question on the how do you expect the model to be modified with other metallic alloys, so steel, aluminum, etc., with different energies in the bonds?
So as the correction depends on the two constants A and B, we expect that this constant A and B will vary for different types of alloy, depending on the specific heat and the density of the material, but to be consistent or accurate enough with the level of error between 2.5%, 3% for as long as the thermal and density properties of the alloys are in the same category. So for example, if we were investigating steel, we could calibrate the constant A and B for a particularly ductile steel or for a range of ductile steel, and then assume and verify that these corrections are valid for a wide range of steel alloys or aluminum or copper. But it's important that the heat capacity and the density of the material have to be on the same range. Otherwise, the coefficient A and B are different.
Okay, thank you. Another one about the adiabatic heating. So can you determine the adiabatic heating threshold with IR measurements?
So well, for simplicity, we assume a constant Taylor-Kinney coefficient. In reality, we know that's not the truth. There is a lot of research that proves that this is indeed variable with strain. So to make sure that despite this this simplification, that the simulation were representative of the experiments, we also matched the maximum adiabatic heating temperature rise of the sample and of the simulation and of the experiment. I'm not sure this was the question. If I didn't reply it, please rephrase it, and I will be happy to reply again.
Yeah, you can write it down here, or contact us again if you want to talk a bit more about this. Another question that just popped up. You've got quite high resolution images of the neck. Are they good enough to use correction factors, for example, Brickman, based on the neck shape?
Yes, the resolution of the specialized imaging Kirana is good enough. Is definitely good. It operates at full resolution, regardless the frame rate. So it is good enough up to 5 million frames per second. We use typically for ductile alloys is used between 500,000 frames per second and 1 billion frames per second. But if the material would be more brittle or higher strain rate, it still keeps the same resolution. Nowadays, the technology of high-speed cameras have been pushed further. There is a wide range of cameras, not only this particular camera, but I can name few providers, a few producers that can, for example, some of the big names in the industry are Phantom and far-sighted photon cameras that are still also good enough and actually as good as to capture the shape of the necking profile at high strain rate.
What kind of spatial resolution did you get at that high frame rate?
Now, it's a bit, I don't use the specialized imaging Kirana, but if I'm correct, is about in the region of, well, actually, let's double check very quickly. I think
our imaging is always a few steps behind visible imaging, of course.
So, well, it is in the region of 1,000 times 600 pixel, if I'm correct. Okay. Now, I don't want to browse at the moment, but I think is
in that range.
Part. Yes.
Okay. Great. That's pretty good. That really high frame rate. I think that's it for our questions. So I'll just say another big thank you to Antonio for coming, giving us that really interesting talk. If you have any more questions, if you want to talk in person, contact us. I'll put back our webpage up here, and if you, no, I have to take back control. Sorry.
No worries, no worries. It was the. Okay, I can close the presentation. Do you have now control the screen? Perfect. And I will just, okay, I can see you now. Perfect.
Perfect.
Well, so thank you for inviting me.
Very much.
And please also in the audience, get in touch if any question may arise later on after. Or if you have any common interest in experimental mechanics.
Absolutely. So thank you very much, everyone, and have a great day.
Bye.